Hello, I'm Ilya Trofimov from Yandex Data Factory. And first of all, I would like to thank organizers for invitation to give a talk here at this conference. And my presentation will be about doing distributed coordinate descent for logistic regression with regularization. And it is joint work with Alexander Genkin. Okay, so this research about doing large-scale machine learning. And large-scale machine learning, it is when big data meets machine learning. And big data now is everywhere in all top internet companies like Yandex, Google, Facebook, Microsoft. And as we heard from other talks and many other applications in astrophysics, biology, and so on. Okay, so there are many applications in practical areas. And large-scale machine learning problems often have some common traits. A large number of training examples and high dimensionality are common. And also data sets are often sparse. And often data sets don't fit a memory of a single machine, so these data sets should be handled by a cluster, by distributed systems. And also, for a huge data sets, linear methods for classification and regression are widely used. And there are two main reasons for doing it. First of all, training and testing for linear models are much faster than for nonlinear ones. And the second reason is that, as I said earlier, high-dimensional big data are often high-dimensional, and high-dimensional data sets are often rich, and nonlinearities sometimes are not required at all. Okay. So it is the motivation, and in this research we worked with binary classification, where the goal is to predict a binary class label given a feature vector x. When I talked about linear models, I meant generalized linear models. So many statistical models fall into this family, like logistic regression, linear regression, and probit, Poisson, and so on. And in this research, we worked with widely used statistical model, logistic regression, for binary classification. Okay, so this slide shows the final, the formal definition of logistic regression. And logistic regression is trained by maximizing log likelihood on training data set, or it is equivalent minimizing the negated log likelihood. It is empirical risk on training data set. Okay, so from this point, when we fixed logistic regression and we fixed a training method, we need to solve the optimization problem. And in many practical applications, we want to use regularization. So we need to optimize this function and to find optimal beta. Okay, there are two main widely used kinds of regularization, and it is L2 regularization and L1 regularization, which is more interesting from my point of view because it provides simultaneously regularization and feature selection. Okay. So what do we have in case of L2 regularization? We need to minimize smooth convex function, and it is not easy, but it is better than L1. So for smooth convex functions, and particularly, we're interested in large data sets. So it is large optimization problem. And these methods are commonly used for large optimization. And particularly, we're interested in running these algorithms in parallel in distributed system. And so parallelization of SGD is tricky. Conjugate gradients and LBFGS, they have almost linear speedup. And the last line here is coordinate descent methods, which works very well on a single machine, but there are almost no research about running them in parallel in distributed system. Okay, and as far as L1 regularization is concerned, it leads to minimization of non-smooth but still convex function, and it is harder to do. And what do we have here? We have some set of optimization techniques which are used on a single machine. And I want to notice that coordinate descent methods, they work well also for L1 regularization, but it is not well studied how to run them in parallel. Okay. So the goal of this research is to adapt coordinate descent algorithms to distributed systems, because they are flexible, they can handle different regularizers. And when we work with coordinate descent, it is natural to split data set by features, not by examples, but by features. It's sometimes called vertical splitting, so that each machine is responsible for some subset of input features. Okay, so each machine is responsible for some subset of input features, and it will make step at each iteration over this subset. And here there are two main questions. First question, how to compute this step. And the second question, how to organize synchronization and communication between machines, how to do it effectively for big data. The first question, in this research, we did one step of the GLMNet algorithm, which is one of the best coordinate descent method for a single machine. But at this step, any other method, I think, will work well. And the second question turned out to be more complicated. Maybe the most simple idea is to sum up all steps from all machines, all delta beta. But it turns out that these steps may come in conflict. So that target function which we want to minimize, it may occasionally increase. So the solution here is to make some step size, introduce step size, and to guarantee convergence of the whole algorithm, we should select step size satisfying the Hermite rule. So here is formal definition of this rule. Okay, so here we see another problem. We need to check that these conditions for Hermite rule hold and do it in distributed system. So we need to calculate the negated log likelihood and regularizer. So the main problem is how to do it effectively. So okay, as far as log likelihood is concerned, we keep vector beta x synchronized among machines. So this is vector with size of training examples. Okay, so it is predictions at all points. And between machines, we transfer only vectors delta beta x. So the vectors again size of n. And the regularizer for L1 and L2, these regularizers are separable. So we can calculate parts of regularizers separately on all machines and then sum up these scalar numbers. So the total communication cost of our algorithm is proportional to number of training samples and number of machines. Okay. This slide presents the whole algorithm. So I have already summarized it. So it is formal definition of the algorithm. Okay. Another interesting problem which we faced during this research is a slow node problem. And it is common in distributed machine learning and maybe in broader class of distributed algorithms. So what it means, if we make some iterative computations on cluster, the typical algorithm is following. We make some calculations on all machines and then need to synchronize the result. Okay, and here we see some problem because if one machine is very slow, all other machines should wait for this slow one. Practical evidence suggests that it is really very bad problem. It may slow down the algorithm significantly. So how we solve this problem? The solution is following. Each machine may update during iteration only subset of features which it is responsible for. So only some smaller set. And these subsets are defined dynamically so that each machine will spend approximately the same time at each iteration for calculations. So that slow machines, so that fast machines should not wait the slow ones. And when doing many iterations, each machine will touch all input feature. So each machine optimizes, makes steps over features cyclically. Okay, we call this technique asynchronous load balancing. We have some theoretical results for our algorithm. First of all, we call this algorithm DGLMNet, so distributed GLMNet. And it turns out that at each iteration, this algorithm optimizes the quadratic approximation to target function. So it is a quasi-Newtonian algorithm. And here H is a block diagonal approximation to the Hessian, because we initially split it input features by blocks and assign them to machines. Okay, and second result is that this algorithm converges at least linearly, so at least linear speed of convergence. Okay, we did some series of numerical experiments with several data sets. And we used 16 machines in Yandex, from cluster in Yandex. And we compared our algorithm with some competing ones, particularly online learning LBFGS and the ADMM. We used sharing technique, which also assumes feature splitting. So we implemented ADMM also in our program. Okay, so we wanted to be as fair as possible, so we optimized and tuned the competing algorithms for maximum performance and selected best regularization parameters. And also we did all tests 9 times because running time at cluster can vary from run to run. So we take the execution time with the median time. Okay, here are some results. So we have much more plots in our paper. So it is how fast it optimizes, how fast it reaches the testing accuracy. And you see that the blue line here is at the top. So it is our algorithm with load balancing trick. Okay, so there are more plots in the paper. I have included only 2 ones, two plots. So what conclusions? What we have learned that DGLMNet is faster than several state-of-the-art algorithms on sparse high-dimensional data sets. Actually, for one dense data set, this algorithm was a bit slower than LBFGS, but on sparse data set, it is better. So the natural extension of this algorithm is to other separable regularizers, and also surely other kinds of generalized linear models. So it can be easily extended. Okay, and at last, we are thinking about extending this algorithm to doing boosting in distributed settings. So boosting builds a target function as a sum of weak learners. So, and boosting does it iteratively. And the idea here is to train weak learners independently on all machines on different subset of input features, and then sum up these weak learners. And to ensure and guarantee convergence, we should multiply it by the step size. So many algorithms hold, which we developed for the DGLMNet algorithm. Okay, so the software implementation is publicly available, and also I can send you a paper if you're interested in this research. Okay, thank you.
Thank you, Ilya. Let next speaker get ready, Mish. Questions? Oh, please.
So do you assume any independence between the variables that compose the problem? I believe not.
This method itself does not assume any dependencies, relations between input features, if you mean it.
So when you separate into different features going into a different machine, then you don't have...
Yes, I get it. We did the splitting at random splitting between machines by a hash function.
But you lose the chance of having only a single solution. So this is not guaranteed anymore. Different splits can cause different solutions.
We have a proof of convergence that this algorithm will converge to the solution. So we need to optimize a convex function, which even strongly convex function, which has unique minima. So any good algorithm will converge to the same solution, and we have a proof of convergence. Yes, it will be different. Maybe speed of convergence will be a bit different for different splits. but it will eventually converge to the same point.
The target function is different.
No.
Target function is different if you have a different block approximation to the Hessian. The approximation.
No. Target function is always the same. It is a log likelihood plus regularization.
Well,
like this.
theorem 1, bring it up.
The steps will be different for different splitting.
Yeah.
Each iteration is equivalent to. So iterations will be different, and steps will be different. But final solution will be the same.
So you say the final solution is not dependent on H, which stands for approximation to the Hessian?
This H, it will be different in different points for different splits.
Yeah.
So H defines the step on a particular iteration.
So it changes between iterations? You have different splits on different iterations?
We have different H at different iterations.
Because of different split? Or not?
Well, no.
All right.
Maybe we can talk later. Maybe.
Please do. There is another question there.
Thank you for a practical talk. My question is, how well does the algorithm scale practically?
Yes, good question. So it does scale when adding machines, but it eventually reaches some limit, some flat line. So yes, some limit exists for each data set. This limit is different limits.
So what's your experience with scaling?
The more sparse data set is, the better is speed up. So for one data set, it was almost linear. Maybe I don't remember 32 times speed up when I used 32 machines. And for dense data set, maybe only 8 times speed up.
Okay, thank you.
Mm-hmm.